Today we're going to talk about limits of trigonometric functions. Limits of trig functions are nice because if a is in the domain of the trig function, then you can use direct substitution to solve it. For example, the limit as x approaches a of the sine of x would just be the sine of a. So let's look at a couple examples. If we wanted to take the limit as theta approaches pi over 4 of the cotangent of theta, we'll try direct substitution. That would give us the cotangent of pi over 4, which, as most of you know, is 1. But if you didn't, you can change that into cosine of pi over 4 over sine of pi over 4. The cosine of pi over 4, you should know, is root 2 over 2. Same as the sine of pi over 4 is also root 2 over 2. And root 2 over 2 divided by root 2 over 2 will give us 1. If we want to take the limit as theta approaches pi over 3 of 1 plus the cosine of theta over 2 plus the cosecant of theta, again, we can do our direct substitution because pi over 3 is in the domain of the cosine as well as in the cosecant, and that gives us 1 plus the cosine of pi over 3 over 2 plus the cosecant of pi over 3. The cosine of pi over 3 is 1/2. The cosecant of pi over 3 is 2 root 3 over 3. And then you can find your common denominator to combine and simplify your answer to get 9 over 12 plus 4 root 3. Now let's look at this next example here. We have the limit as x approaches 0 of the sine of pi over x. As you see, we cannot do direct substitution here because that would give us 0 in the denominator and that's not defined. So what we would ordinarily do is make a table of values and plug in values getting really close to 0 from the left and the right. So plugging in like negative 0.1, negative 0.01, negative 0.001, or 0.1, 0.01, 0.001, and see what the function does. Now I urge you to take out your calculator and do these calculations, and you will see that the sine of pi over negative 0.1 would come back as 0. So would the sine of pi over negative 0.01. So would the sine of pi over negative 0.001. And the same thing for these three values. So what does this tell us? This tells us that we would think that the limit as x approaches 0 of the sine of pi over x would be 0. But here's another set of numbers. Negative 2 over 23, negative 2 over 203, negative 2 over 2003. These are getting significantly close to 0 coming from the left. 2 over 21, 2 over 201, 2 over 2001. That's getting really close to 0 coming from the right. But when you plug those values in for x, each one of those is going to give you an output of 1. So this would tell us that the limit as x approaches 0 of the sine of pi over x would be 1. But look at these set of values here. Negative 2 over 21, negative 2 over 201, negative 2 over 2001. These are getting significantly close to 0 from the left. 2 over 2003, 2 over 203, 2 over 23. These are getting significantly close to 0 from the right. And when you plug those values in, you get negative 1 for each one of those. So that would tell us that our limit as x is approaching 0 of the sine of pi over x would be going off to negative 1. But in order for a limit to exist, if you look back at our definition of a limit, is that as x gets significantly close to the a value, the function gets significantly close to a single finite value. But as you can see, we're not approaching a single finite value. Here we're approaching 0, here we're approaching 1, and here we're approaching negative 1. So we would say that this limit does not exist. If you were to look at the graph of the sine of pi over x, it's an oscillating function that goes up and down, up and down, up and down, and it goes up and down really quickly the closer you get to 0. I have a theorem for you. This is called the Squeeze Theorem. So if f of x, g of x, and h of x are functions that satisfy that g of x is always less than or equal to f of x, and f of x is always less than or equal to h of x, for x not equal to a, in an open interval containing a, and if we knew that the limit as x approaches a of g of x gave you L, and also that the limit as x approaches a of h of x also gives you L, so the limit of this lower function gave you L, and the limit of this higher function here gave you L, then the squeeze theorem tells you that the limit of this middle function, the limit as x approaches a of f of x, would also give you L. So let's look at this example here. The limit as x approaches 0 of x times the sine of 1 over x. We clearly can't do direct substitution because that 1 over x would be 1 over 0, which is undefined. But what do we know about sine? We know that the domain of sine is all real numbers. You can plug in anything you want, but the range of the sine is always between 1 and -1. So we can start off by saying no matter what we put inside here for 1 over x, the sine of it is always going to be between -1 and 1. So -1 is always going to be less than or equal to the sine of 1 over x is always going to be less than or equal to 1. Well, that doesn't help us because we've got this extra x here. So let's multiply x to this entire inequality, right? So -1 times x gives us -x, x times the sine of 1 over x, and then x times 1 would give us x here. Now, if I took the limit as x approaches 0 of -x, that gives me 0, and the limit as x approaches 0 of x gives me 0. Well, since we have the x sine of 1 over x stuck in between those two functions, by the squeeze theorem, we can see that the limit as x approaches 0 of x times the sine of 1 over x must also be equal to 0. There are two really important trig limits that we are going to talk about. The first one is the limit as x approaches 0 of the sine of x over x. Again, we can't do direct substitution because of this over x thing right here. So we're going to kind of build up to what it is. So right here, this is my nice unit circle here. I've got a nice unit circle here, radius 1. And so any ordered pair x comma y is going to be the cosine of theta comma the sine of theta. Okay, so here's this one right here. So I'm marking this ordered pair as cosine of theta, sine of theta. So now I need to figure out what this ordered pair is. Now I know that you can see that it's 1 comma the tangent of theta, but I want you to see where that came from. Right here, so I've got this kind of trapped right here, this little arc in here. I can form these two triangles. And look at these two triangles. This first triangle right here that I have drawn here, that ordered pair is cosine comma sine, which means that the x value we went over cosine of theta, and the y value we went up sine of theta. So it's this right triangle right here. This bigger triangle here, we can see the base of it is going to be 1, but the height of it, we don't know what that is yet. But this is forming similar triangles because these angles are the same, right? 90 and 90. This angle is the same for both of them. So then this upper angle here must be the same for both of them. So we have similar triangles. And if we remember about similar triangles, the ratios of their lengths of their sides are going to be the same. So cosine over 1 will be the same ratio as the sine over whatever this question mark is here. So then I'll cross multiply. So the cosine times question mark is going to be equal to the sine of theta times 1. Solve for your question mark, divide both sides by cosine, and you can see that that question mark, this height right here, is sine over cosine, which is tangent. So we have this tangent right here. So that's where this ordered pair came from. All right, so now I've got this wide triangle right here that I just kind of made up here, this wide triangle that goes up to cosine comma sine, and then it comes down to this corner here, so it shares that base 1. We have this larger rectangle triangle right here, and then this little pizza slice here, this arc that I came up with here, is wedged in between the two. So here's that first triangle here that has a base of 1. This ordered pair is cosine comma sine. Here is that sector, that arc thing that we had here, where this is the angle theta, and here is that larger triangle. Well, as you can see, based on this picture right here, this triangle's area is smaller than this sector's area is smaller than this bigger triangle's area. So the area of this triangle is less than or equal to the area of the sector, which is less than or equal to the area of this triangle. The area of a triangle is 1/2 the base times the height, and the area of a sector is 1/2 the radius squared times the central angle. The height of this triangle is going to be sine, and the base, since it's a wider triangle, is still 1 here. This sector is going to be 1/2 the radius is 1 squared times theta, and this triangle, 1/2 the base, which is 1, times the height, which is tangent of theta. So now I am going to multiply everything by 2 to get rid of those 1/2s. And when I do, I have that the sine of theta is less than or equal to theta is less than or equal to the tangent of theta. Now, I'm going to write this differently. I'm going to rewrite this as 1 over tangent of theta is less than or equal to 1 over theta is less than or equal to 1 over sine of theta. Because I thought somebody might have a question on that, I showed it to you up here. If the sine of theta is less than or equal to theta, then I can divide both sides by the sine of theta, and I have 1 is less than or equal to theta over sine. Then I can divide both sides by theta, and you can see that 1 over theta is less than or equal to 1 over sine of theta. Another way to look at it, if I had theta is less than or equal to tangent of theta, then I can multiply by the reciprocal of theta, so multiply both sides by 1 over theta. 1 over theta times theta would give me 1, and this would give me the tangent times 1 over theta. And then I can divide by the tangent of theta, and I get 1 over tangent of theta is less than or equal to 1 over theta. So that's what I did to get this expression right here. So now what I'm going to do is multiply everything by the sine of theta. With an inequality, you can do whatever you want as long as you're doing it to everybody. Keep it fair. So then when I do that, I have sine times 1 over tangent. Well, 1 over tangent is the reciprocal of tangent, which is cosine over sine, is less than or equal to the sine of theta over theta, is less than or equal to the sine of theta over the sine of theta, which is 1. Notice these signs are going to cancel. So when I reduce this, I have the cosine of theta is less than or equal to the sine of theta over theta is less than or equal to 1. Well, let's take those limits. Let's take the limit as theta approaches 0 of the cosine of theta. That would give me the cosine of 0, which is 1. And the limit as theta approaches 0 of 1 would also just be 1. So since this limit here was 1 and this limit here was 1, by the squeeze theorem, the limit as theta approaches 0 of the sine of theta over theta must be equal to 1. So that's our first special limit that we have here, that the limit as x approaches 0 of the sine of x over x is 1. The second important limit that we're going to talk about is the limit as x approaches 0 of 1 minus the cosine of x all over x. Again, direct substitution isn't going to work. So what I'm going to do is actually multiply the top and the bottom by the conjugate. So I have 1 minus the cosine of x over x. I'm going to multiply the top and the bottom by 1 plus the cosine of x. Now when I do this, I would end up foiling these two numerators, right? 1 times 1, then I would have plus cosine of x minus cosine of x minus cosine squared. The positive and negative cosine will cancel, and so I have 1 minus cosine squared of x over x times 1 plus the cosine of x. 1 minus cosine squared of x, from the Pythagorean identity, that is equal to sine squared of x, so we have that here. Sine squared is sine times sine. So now I can break these up into two different things being multiplied, and I have the limit as x approaches 0 of the sine of x over x times the sine of x over 1 plus the cosine of x. Limit laws say I can take the limit of this times the limit of this. So I'm going to take the limit as x approaches 0 of the sine of x over x times the limit as x approaches 0 of the sine of x over 1 plus the cosine of x. This is that first special limit we just proved. This limit is equal to 1. Here I can use direct substitution. The sine of 0 is 0 plus over 1 plus the cosine of 0 is 1. That gives us 0 over 1 plus 1, which is 0. Anything times 0 is 0. So this limit here, the limit as x approaches 0 of 1 minus the cosine of x over x is 0. These two special limits will come up in other lessons that we do with calculus of trig, and they are very important. So let's do some applications of them. So if we wanted to look at the limit as x approaches 0 of 5x over the tangent of x, tangent of 0 is 0, so that would give us 0 in the bottom, so we can't do direct substitution. But the limit as x approaches 0 of 5x times over the tangent of x is the same thing as the limit as x approaches 0 of 5x times 1 over tangent of x. This 5 is a coefficient, I can pull it out. So I have the limit, I have 5 times the limit as x approaches 0 of x times 1 over tangent, which is sine over cosine. X is the same thing as 1 over x, right? 1 divided by 1 over x. And so when I multiply these together, I have 5 times the limit as x approaches 0. I have that sine of x over x times 1 over cosine of x. Limit laws say I can bring this limit to each of these separately. So that's going to be 5 times 1 over the limit as x approaches 0 of the sine of x over x times the limit as x approaches 0 of 1 over cosine of x. The limit as x approaches 0 of the sine of x over x is 1. It's the special limit. And here, direct substitution, the cosine of 0 is 1. So this gives me 5 times 1, or 5. Let's look at one more example. The limit as x approaches 0 of sine of 3x over 4x. This isn't quite that special limit, but it's kind of close. Unfortunately, these don't match exactly, but we can make them match. Let's multiply the top and the bottom by 3. So we have the limit as x approaches 0 of 3 times the sine of 3x over 3 times 4x. So I'm going to switch the roles of these 3 and 4. I don't need the 3 and 4, so I'll pull those out here. And I have the limit as x approaches 0 of 3/4 times the sine of 3x over 3x. So now what we can do is we can let u be 3x. So then if x is going to 0, then 3x would also be going to 0, which means that u would be going to 0. I can pull this 3/4 out of the limit and rewrite this as the limit as u approaches 0 of the sine of u over u. This is that special limit that is equal to 1, so this limit turns out to be 3/4. That's it for this. I'll see you next time.